Welcome back to our AI paper discussions, your shortcut to staying current with AI research. Today, we're tackling a huge challenge in large language models.
That's right. We're looking at how to handle massive context lengths without, well, grinding everything to a halt because of memory and speed issues.
Exactly. We're diving into a paper called ChunkLLM, a lightweight pluggable framework for accelerating LLMs inference. Sounds promising for anyone working with these models.
It really is. It addresses some fundamental architectural limitations head on.
Okay, fantastic. And for everyone short on time, let's do the quick 1-minute summary right up front. What are the absolute key takeaways here? So the main problem, and it's a big one, is that standard transformer attention scales quadratically. ON2.
Yeah.
Double the context, 4 times the compute. It just kills speed and eats memory, especially when you're talking like 100K tokens or more.
And the solution presented here is ChunkLLM. It's designed as a plug-and-play framework. You take your existing big model, say a Llama or a Quinn, keep it frozen, and just attach 2 small trainable modules, a QK adapter and a chunk adapter.
Right, and the mechanism behind it is quite smart. It's about dynamic chunk selection. The chunk adapter figures out where meaningful semantic breaks are in the text.
And then the QK adapter compresses the information and learns to pick only the most relevant chunks from memory for the attention calculation. So you skip that massive full context computation.
The result highlights are pretty impressive, aren't they?
Oh, definitely. They're reporting up to a 4.48x speedup compared to a standard transformer when dealing with really long text, around 120,000 tokens.
Wow.
And crucially, it does this while maintaining about 98.6% of the original model's performance on long context benchmarks. Plus, it slashes the KV cache size needed, down to about 48% retention. Huge memory savings.
That plug-and-play aspect combined with those results, that's why this feels so important. It suggests a way to get these efficiency boosts without needing to, retrain these giant foundation models from scratch, which is just incredibly expensive.
Precisely. It connects directly to the big picture challenge. How do we make these incredibly powerful models practical and affordable to deploy, especially as we push towards, say, million token context windows? This paper offers a potential engineering pathway.
It's tackling that complexity problem, yeah. Okay, let's unpack that core limitation again. This quadratic scaling, the ON2 thing. What does that actually feel like if you're trying to run these models?
Well, it feels slow. Really slow inference latency. And it feels like you're constantly running out of memory, especially VRAM on GPUs.
All right.
Because every single time the model generates a new token, the standard approach needs to look back and calculate attention scores against every single previous token in the context.
Even tokens from way back?
Yep. So as that sequence grows, maybe tens or hundreds of thousands of tokens long, the computation needed just balloons quadratically. It's the fundamental bottleneck for long context inference. We need something smarter.
And researchers have been trying different things, right? The paper touches on a few prior approaches. What were the main categories, and maybe why didn't they fully solve the problem?
Sure. Broadly, you can think of 3 main lines of attack. First, there are completely new architectures. Think linear attention models like Mamba, RWKV, RetNet.
Okay.
These replace the standard self-attention mechanism entirely. They can be much more efficient, computationally speaking. But the big drawback is architectural difference. If you've already invested millions in training a huge transformer model.
You can't just swap in a Mamba layer.
Exactly.
Yeah.
Converting it is often impractical or requires starting over, training a new model from the ground up. Very expensive.
Okay, so new architectures are tough for existing models. What about trying to make the standard attention more efficient, like sparse attention?
Right. Sparse attention methods try to limit which tokens attend to which other tokens. Things like using a fixed sliding window.
So only look back at the last, say, 4,000 tokens.
Kind of like that, yeah. Or maybe some other fixed pattern. The issue there is they often lack flexibility. A fixed window might miss crucial information that appeared much earlier in a very long document. Their performance can be very task-dependent, limiting generalization.
Makes sense. Which brings us to the third category, dynamic sparse attention, which seems closer to what ChunkLLM does. But what were the problems with earlier dynamic methods, like one they mentioned, SEP-LLM?
Well, early dynamic methods had their own issues. Some used fixed chunk lengths, just chopping the text every n tokens.
Which could cut a sentence right in half, I guess. Bad for meaning.
Precisely. Breaks semantic integrity. Others tried using separators like periods to define chunks dynamically. But that can be ambiguous. Think periods in abbreviations,
Yeah,
right?
true.
And a bigger issue, especially with methods like SebLM, was that they often still needed to figure out which chunks to attend to for every single token being generated. That recalculation itself adds a significant overhead, kind of undermining the efficiency gains you're hoping for.
Okay, so this is where ChunkLLM comes in with its specific design. The idea of keeping the main model frozen and just adding these two small trainable adapters feels quite elegant. Let's start with the first one, the chunk adapter. What's its job?
The chunk adapter is basically the boundary detector. It's a very lightweight module, just a single feed-forward neural network layer trained as a classifier.
A classifier. What's it classifying?
Its only job is to look at a token and decide, is this token the last token of a meaningful semantic chunk, like the end of a sentence or a coherent phrase? It outputs a simple yes or no, a 0 or 1.
And they strategically place it, right. It connects to the output of the very first transformer layer. Why there?
That placement is key. The bottom layers of a transformer are generally understood to handle more of the syntactic structure and local patterns in the language.
Ah, so it's looking for grammatical cues for sentence endings and things like that.
Exactly. It tries to identify those boundaries based on the fundamental structure before the model builds up more complex, abstract meaning in the higher layers.
Yeah.
This helps ensure the chunks it identifies are actually semantically coherent units.
Makes sense. And how did they train it to recognize those boundaries?
They used a pre-existing tool, PSBD, which is designed for sentence boundary detection, to automatically label a large dataset, FineWeb IDU in this case. Then they trained the chunk adapter using a standard binary cross-entropy loss, basically teaching it to predict the labels generated by PSBD.
So leveraging an existing linguistic tool to inject that knowledge. Clever. Okay, what about the second module, the QK adapter? It handles compression and scoring.
That's right. The QK adapter works in parallel with the standard query, Q, and KK computations that happen in every layer of the transformer.
So it doesn't replace them?
No, it supplements them. Its primary role is feature compression. It takes the high-dimensional internal representations from the model and squishes them down into a much, much smaller dimension. Let's say from dimension D down to dk, where dk is way smaller than D.
And that compression must be a big part of the efficiency gain, right?
Absolutely. Because these compressed representations, Q bar and K bar as they call them, are then used to calculate the attention scores between chunks. Since the representations are tiny, calculating these scores is computationally very cheap compared to full attention on the original high-dimensional vectors. It serves both to compress and to generate the chunk attention scores. So we have these two small adapters. But the main LLM, the backbone, is frozen. It's not learning anything new. How do we make sure these tiny adapters actually capture the important knowledge from that giant frozen model?
Yeah, how do they learn what's important without retraining the whole thing? This is where that attention distillation comes in, isn't it?
Exactly. Attention distillation is the process they use specifically for training the QK adapter. The goal here is to teach the adapter how to effectively select the most relevant past chunks, maximizing the recall of key information.
So it's like a student-teacher setup.
Precisely. The student is the attention mechanism within the QK adapter, the one that calculates scores between chunks, as in the paper. The teacher is derived from the original full attention mechanism of the vanilla transformer.
Yes. So you run the original model, see what it paid attention to with its expensive full attention.
You aggregate that information, essentially finding out which past tokens the original model thought were most important for generating the next token.
And then you train the little QK adapter to mimic that pattern, but using its compressed chunk representations.
Exactly right. They use callback libeler divergence, or KL divergence, as the loss function. It measures how different the student's attention distribution ACE is from the teacher's AT. The training process forces S to get closer and closer to AT, effectively distilling the knowledge of what's important from the big model into the small adapter.
That's really neat. And this whole approach, frozen backbone, tiny adapters, distillation, makes the training incredibly efficient.
Hugely efficient. We're talking about only fine-tuning these adapters. For models like Qwen 2.57b or Llama 3.18b, the total number of additional parameters is tiny, something like 14.7 million for Qwen, 21 million for Llama. That's, a drop in the bucket compared to the billions in the base model.
Minimal training cost, minimal time.
Minimal everything. And here's the really striking part. They trained ChunkLLM using only context of 4,000 tokens.
Only 4K. But the results were for much longer contexts.
Yes. Despite being trained only on 4K contexts, it showed strong performance way out to 120,000 tokens during inference. That really validates the power of this distillation approach for scaling context capability without needing correspondingly massive training data or compute.
Okay, so training is efficient. Now let's switch to inference time when you're actually using the model. Speed is critical here. How does ChunkLLM maintain speed, especially during long generation?
This is where a key observation they made comes into play. They call it Intra-Chunk Attention Consistency, or ISAC.
ICC. Okay, what's the consistency they found?
They noticed that when the model is generating tokens that belong to the same semantic chunk, say, continuing a sentence that already started, the set of past chunks it pays attention to tends to remain remarkably stable.
So it doesn't suddenly decide to look at a completely different set of old information mid-sentence?
Generally, no. The significant shifts in which chunks are most important tend to happen primarily when the model crosses a chunk boundary, when it finishes one semantic unit and starts the next.
I see. And that pattern, that ISAC see, is something they can exploit for efficiency.
Exactly. It's the core of their inference speedup. Because of ISAC, they don't need to recalculate which chunks are the most important for every single token.
Only when the chunk adapter signals a boundary.
Precisely. If the chunk adapter says, nope, not a boundary token, the system just reuses the previously selected set of top 8 chunks. No expensive recalculation. The computationally heavy step of using the QK adapter to score all chunks and select the top K only happens when a boundary is detected by the chunk adapter. That saves enormous amounts of computation during long sequences.
That makes a lot of sense. Okay, so when a boundary is detected, it does the top K chunk selection. How does that work? And how does it handle the fact that different layers might have different ideas about which chunks are important?
Good question. When a boundary is hit, each layer's QK adapter calculates attention scores between the current token's compressed query, Q-bar, and the compressed keys, K-bar, of all the previous chunks stored in memory. Each layer then identifies its own local list of the top K most relevant chunks based on these scores.
But layer 5 might pick different chunks than layer 20, right?
It might, yeah. Different layers capture different levels of abstraction. To reconcile this, they introduce a voting mechanism.
Like an election for chunks?
Sort of.
Yeah.
Think of it as a consensus mechanism.
Yeah.
It takes the top K chunk lists proposed by each individual layer and aggregates them. It essentially holds a vote across all layers to determine the final global set of top chunks that will actually be kept in the KV cache for the next token generation steps.
So it ensures the final selection isn't biased by just one layer's perspective, but reflects a consensus across the whole model depth.
Exactly. It helps maintain the quality and relevance of the selected memory by smoothing out potential discrepancies between layers.
Okay, let's get to the results. The proof is in the pudding, as they say. How did ChunkLLM actually perform on standard benchmarks, especially for long context tasks?
Pretty well, according to the paper. They tested it on LongBench, which is a common suite for evaluating long context performance. Compared to baselines like Streaming LLM and SepLM, ChunkLLM generally came out on top, achieving an overall average performance that was about 98.64% of the original vanilla model score.
So very little performance degradation despite the approximation.
Right, and they specifically highlighted its strength in tasks like multi-document question answering. They argue this is where the attention distillation really pays off, because it helps the model better recall and utilize key information scattered across long documents.
And what about the memory side? That KV cache reduction is crucial for deployment, right?
Absolutely critical. They reported that for the Quinn model, ChunkLLM reduced the KV cache retention rate down to just 48.58%. That's less than half the memory footprint compared to storing everything.
Wow, nearly a 2x reduction.
Yeah, and significantly lower than the other methods they compared against too, while, as we said, maintaining that high performance. This directly translates to needing less VRAM, which makes deploying larger models much more feasible.
Okay, the ultimate torture test for long context is often needle in a haystack, right? Finding one specific piece of information buried deep. How did it do there?
It held up surprisingly well. For the Llama 3.18b model using ChunkLLM, they reported a score of 93.84 on the NIH task at a 64,000 token context length. The vanilla model scored around 99.4, so there's a small drop, but 93.84 is still excellent retrieval performance under such heavy approximation.
And how did that compare to, say, SepLM?
That comparison was quite stark. The paper notes that SepLM's retrieval ability basically collapsed once the context got longer than about 12,000 tokens. ChunkLLM's combination of semantic chunking and distillation seemed much more robust for finding that needle.
That's a significant difference. Okay, now the metric everyone loves, speed up. What were the numbers?
The headline number is that maximum speedup of 4.48x for the Llama model, Observed during the later stages of generating a very long sequence, around 110K to 120K tokens. For Quinn, it was up to 3.84x.
But is it consistently faster or just at the very end?
That's the other key point, the stability. They show graphs where the inference time for the vanilla transformer just keeps climbing linearly as more tokens are generated. But ChunkLLM's time cost stays remarkably flat across that whole 120K range.
Which is that ICAC optimization kicking in, right?
Right.
Avoiding calculations.
Exactly. It prevents that linear slowdown, maintaining persistent stability and time consumption. That's huge for predictable performance.
Now, there's usually no free lunch. When you approximate attention like this, does it hurt the model's understanding of language? What about perplexity, PPL?
There's a slight trade-off, yes. The perplexity for ChunkLLM was a bit higher than the vanilla model for Llama. They reported 12.89 versus 11.93 for vanilla.
So slightly less certain about predicting the next word.
A tiny bit, yeah. But given the massive speed up and memory reduction, that small increase in perplexity seems like a very acceptable, even beneficial trade-off for most practical applications. And importantly, they also checked performance on standard short context benchmarks.
And did it forget how to handle normal tasks?
Nope. It performed almost identically to the vanilla models, achieving around 99.6% to 99.8% of their average scores on short text tasks. So it seems to maintain its core capabilities across different context lengths. All right, so the overall results look good. But really understand why it works, we need to look at their ablation studies where they take components out to see what breaks.
Good idea. Let's be critical. What happened when they removed that voting mechanism that combines the top chunks from different layers? Was it really necessary?
It seems so. According to their results, removing the voting mechanism caused a noticeable drop of 1.6 points in the overall long bench performance score.
Okay, not catastrophic, but measurable.
Measurable enough to confirm its value. It suggests that layers do sometimes disagree on which chunks are important. And simply taking the chunks from one layer, or maybe averaging them naively, isn't as good as having that explicit cross-layer consensus mechanism. It helps keep the most globally relevant info.
Makes sense. Okay, what about the efficiency star, the ICK pattern? What if they just didn't use it? What if they calculated the best chunks for every single token, even within a chunk?
That's a really interesting ablation. When they turned off the IC case optimization, meaning they updated the chunk selection at every step, they actually saw a tiny improvement in performance, about 0.15 points on long bench.
Oh, so more frequent updates is slightly better for accuracy.
Technically, yes, a very marginal amount. However, and this is the crucial part, doing so made the inference latency 2.12 times higher during that long generation phase.
Ah, there's the trade-off.
Exactly. Disabling ISAC gives you back a minuscule amount of performance, but completely sacrifices the massive speedup. It proves that exploiting ISAC is essential for achieving that balance of near-original performance with dramatic efficiency gains.
Okay, that clarifies the ICAC value. One more comparison. The core idea of semantic chunking versus just using fixed-length chunks. Did the smart boundary detection really matter that much?
It mattered quite a lot, especially for tasks requiring specific information retrieval. They compared ChunkLLM, semantic chunks, to a version they called FixLM, fixed-length chunks, on that 64K needle in a haystack task.
And the result?
Fixed LLM's accuracy was 8.23 points lower than ChunkLLM's. That's a significant drop in retrieval capability.
So just chopping the text up arbitrarily, it really hurts the ability to find things later.
It strongly suggests that, yes, using those semantic boundaries helps ensure that coherent pieces of information aren't accidentally split across different chunks, making them harder for the attention mechanism to piece back together later. The semantic approach is clearly superior for preserving information integrity.
All right, let's wrap this up. Summing up the key takeaways here. ChunkLLM seems to offer a really practical, efficient way to push the context length limits of existing LLMs. The plug-and-play adapters mean low setup costs.
Right, no need for full retraining.
The attention distillation effectively transfers knowledge to keep performance high.
Maintaining that crucial recall ability.
And exploiting that intra-chunk attention consistency, the ICC pattern, delivers substantial, stable speedups during inference.
It's a very neat piece of engineering, balancing performance and efficiency.
Definitely feels like a valuable approach for anyone deploying these models.
Absolutely. And it leaves us with an interesting thought maybe for you listening to the researchers or engineers out there. ChunkLLM's success really hinges on identifying and exploiting that intra-chunk attention consistency to optimize KV cache management. So the question is, given how well freezing the backbone and using lightweight adapters with distillation worked here for attention and memory,
Where else in the transformer architecture might similar strategies apply? Could we design adapters to tackle other bottlenecks, like maybe the computations within the feed-forward networks, to unlock even more hardware acceleration? Something to think about.